Good morning, everyone. Welcome to our lecture in Physical Chemistry 4 on the electronic structure. Last week, we introduced the reasons and the motivations why this electronic structure is a worthwhile topic for chemistry in general and for physical chemistry in particular. We ended on Tuesday with this discussion of the problems that we have when trying to understand the electronic structure, when trying to calculate things. And I used as an example this recent publication in the Chemical and Engineering News, which you see here on the screen. And we then proceeded to do a thought experiment where we were wondering, okay, what would we have to do to formally store the electronic wave function, right? So already within the Born-Oppenheimer approximation, so it's already approximate. But just suppose for this fixed external potential, so fixed nuclei somewhere in space, suppose you would like to solve the full equation, okay? Now, we discussed this, then we would need these 4 dimensions for every electron, and this wave function would have to have this funny property that as soon as you flip the index, right, and as soon as you exchange 2 electrons, the entire thing has to change sign. And then it also has to happen that when you minimize its expectation values with the Hamiltonian, this wave function should then correspond to the true wave function. So it must be in some relation to this Hamiltonian, right? That minimization property you only have for the Hamiltonian, right? It's not for other operators. You have to be able to normalize it, and then a very practical but immensely consequential concern is the amount of data storage you would need. So this would be excessively expensive, as you can see from this little calculation on the back of the envelope at the bottom here. Obviously, this comes along also when you store data, right? You write it to disk, and that will correspondingly also consume electricity. And so in terms of electricity consumption as well as financially, this is hopeless. Consequently, people have devised approximate methods to alleviate this problem, and there have emerged over the decades hierarchies, so different levels of approximations. And typically, the less approximate you are, the more computationally demanding is your method going to be. Now, this course is an introductory course. We will not discuss all these levels of theory. We will discuss some, but not all, and we cannot go in much detail into those we discuss. So this rapidly then becomes an advanced topic, right? But you should have heard about these rough hierarchies. And so I've listed them for you in the field of what's known as quantum chemistry. So there are semi-empirical methods. These include the valence bond theory, molecular orbital theory, which you should be using already also in your general chemistry and your inorganic and organic chemistry classes. That's a level of theory which often you can at least qualitatively do with pen and paper. Then there's Huckel theory, which is already a little bit more advanced, and that's a theory we want to also cover in this course. Then there are computational semi-empirical methods like PM7, MNDO, ZINDO, AM1, OM2. These are methods that have quite complex functional forms, but computationally they are very efficient, and they do approximate difficult integrals or difficult expressions are not written out fully, but rather approximated with easier formulas. So these semi-empirical methods are very fast. They can, for instance, for a typical molecule, they might consume a second or so. As a second level, you have Hartree-Fock. Hartree-Fock is what's known as a mean field theory. Is a very important quantum chemistry method because it includes rigorously the anti-symmetry condition on your wave function, right? So the semi-empirical methods not necessarily have that, and so this is a major step forward, of course. It comes with substantial computational costs. So Hartree-Fock calculation on a large molecule with a good basis function can consume easily minutes, right? On a medium-sized molecule, not very large. After that, we still miss interactions between the electrons, which we call electron correlation interactions, and there are methods devised to increasingly account for them. There are perturbation theory-based methods called Möller-Plössl, second order, third order, or fourth order. Now, in this course, we will discuss the perturbation theory, so you will have a better idea what we are talking about here. There's a question in the chat: what is a medium or large molecule? Well, maybe think of something like testosterone as a something that's sort of medium-sized, right? A couple of fused rings. A large molecule would be a peptide or protein, right? So these are very common molecular species. So with the semi-empirical methods, you can calculate proteins. With Hartree-Fock, a protein would be a challenge, right? Then we have a coupled cluster theory. This is a particular sort of expansion. It's called the Trotter expansion, and that also allows to have a systematic series, which is supposed to become increasingly better. And this method is even more expensive than the Möller-Plössl methods, but it's widely used because it's very, very reliable. It's expensive, but it's reliable, right? So it's a little bit like, suppose with cars. If you want a very nice, reliable car, right, you'd have to invest more money. It will get you from A to B, but things will be still different than in a cheaper car. Then you have configuration interaction, and configuration interaction formally has no approximation, so it very rapidly, as we just discussed for the water dimer, it becomes intractable, and you can simply not do it. So you can do it for a couple of electrons, right? So I don't know, beryllium, the beryllium atom, or a lithium dimer, but then that's it. Afterwards, you have what's known as multi-reference methods. These are methods that allow you to overcome an approximation of the Born-Oppenheimer, the approximation of the Born-Oppenheimer surface that you should be moving on a single surface, right? In fact, you can think, and we briefly mentioned that also, I think, you can think of an excited state as an additional surface. And these surfaces might cross, right? And think about open spin states, right? You can go from a singlet to a triplet spin state in the same molecule, example carbenes. So what happens then to your electronic structure? And this is what the methods devised to deal with such situations are called multi-reference methods. So they basically use multiple solutions for multiple surfaces, and then you can sort of blend them and decide ad hoc which one is the preferable. There's the complete active space where you include all possible excitations, and the question is, how do you select the most relevant excitations? And then there's something known as model chemistry, and we will probably touch on that also later. This was devised by John Popel, one of the founders of quantum chemistry, who also obtained a Nobel Prize in 1998. Now, in physics, actually, sort of similar approximations evolved, and people called them differently, but they do very similar things. And for the sake of completeness, I'm listing them here. So maybe something comparable to semi-empirical methods are the muffin tin or bond order potentials and tight binding density functional theory. Then you have density functional theory that's similar to Hartree-Fock. In some limits, density functional theory, also known as DFT, in some limit, it converges towards the Hartree-Fock solution. Now, within DFT, there are various approximations again, and I've been putting up some acronyms here that stand for these approximations. In particular, there's what's the lowest approximation is the so-called LDA, the local density approximation. Then you have the GGAs, generalized gradient approximations, meta-GGAs, hybrid functionals. Hybrid functions explicitly mix some lower level like a GGA with the Hartree-Fock solution. It turns out this is very beneficial for the accuracy of your predictions. And so you see there are different ways of combining these. Then on the fifth point here, we have many body perturbation methods. This is sort of similar to Möller-Plössl. And then you have a nice method that's also increasingly being used in quantum chemistry called quantum Monte Carlo. This is a Monte Carlo algorithm. Monte Carlo algorithm means that basically you have a random number generator that's being used. If based on the random number, you will change the coefficients, you will change your wave function. If this lowers the energy, you will accept this. If it does not, you will reject it with something like a Boltzmann weight, right, or something like a rate factor. So not necessarily, but with a certain probability, you will accept it. And this probability depends exponentially on your energy, right? So if the energy is, the more it is disfavorable, the exponentially less likely it's going to be that your move will be accepted. So these are ways to solve these electronic structure problems within approximations that are computationally tractable. And so this is how we avoid in practice then this terrible problem here of needing 30 billion Swiss francs just to store a 10 electron wave function. So here's a little bit sort of a cartoon of some of these acronyms I just told you. So the accuracy is sort of on the vertical axis, and on the horizontal axis you see how the cost scales with number of electrons, right? And so this is the sort of a landscape, if you wish, right? So if you are very wealthy, you can move to the right. If you're less wealthy, you can move to the left. Now, if you want to be very accurate, you have to move up. And the lower you are, the less accurate you are. DFT, density functional theory, here with the prefix Kohn-Shah, is a special case because for a constant cost, it gives you extraordinary amount of accuracy, that is something you would certainly like to exploit, right? That's basically a free lunch. And this has been the reason why DFT has become so popular that when John Poble got his Nobel Prize, also at the same time he had to share it with Walter Kohn, and that's the Kohn whose K is in Kohn-Shah DFT, who gave proof of some of the underlying theorems, and we will touch upon that later in this course. Now here's the question: if muffin tin is the same as the Eierschachtel, I'm not sure if that's the same. Yeah, so I think it's rather when you bake these muffins, you have a baking form which has a shape. So it looks a little bit like an Eierschachtel, if you wish, but it's more like a hole, right? Not spikes in between. Anyhow, so each atom is supposed to sit in this. So this is where it comes from. All right. Now, you know, at the university, the point is also to connect you a little bit to what's happening at the research level, right? And even though you're still, even though this is just an introductory course, that's of course the whole point of a university. And so I'd like to mention this this research paper, which I co-authored in 2019. And this was done together with a mathematician, Peter Zaspel, who is the first author here. And he was working with Helmut Habrecht, who is a professor of mathematics in Basel as well. And we worked together to see if we can construct machine learning models that would connect different levels of approximations. And you see here some of these approximations. So this is PM7 I mentioned earlier, Hartree-Fock, MP2, coupled cluster. This is the full configuration interaction, which is intractable, right? So that's sort of a limit we are aiming for. And then we can have a training set of different molecules. And in this paper, we devised a method how we could connect training data at different levels of theory, such that this model can predict the exact solution as well as possible, right? So you see that exploiting these hierarchies, knowing about them, this is very much current research. This paper was the first that demonstrated how to do this. All right, with this, I'd like to come to the last slide of this introduction to the course. So what you should know is basically given by the statement by Paul Dirac, this quotation: the fundamental laws necessary for the mathematical treatment of a large part of physics and the whole of chemistry, quite a statement, are thus completely known, and the difficulty lies only, and that's the understatement, in the fact that application of these laws leads to equations that are too complex to be solved, right? So that is, of course, then you can cynically argue, well, then physics is useless because it might be nice to have the equations, but if you can never solve it, I mean, what good is it to us? And fortunately, so that's sort of the challenge for the theoretician and for physical chemistry, to try to tackle this this aspect, right? And we have made quite some progress. We will not be able to enter much into this progress in this course, since this is an introductory course. But the point of this course is really to help you to grasp what is meant by these fundamental laws. And then trust me, we are making good progress on also making it useful to connect to the experiments. And so if you're interested in that, of course, you should attend the more advanced courses once you're done with this one here. All right, so this concludes my introductory part. Are there any further questions on this first chapter in our course? that doesn't seem to be the case. So this will bring us now to the next chapter. And this is a chapter we'd be doing on a blackboard normally. Instead of that, as a substitute, we will be using the notepad on my iPad here. All right. So here you see the notes which we had for the discussion of the Hermann-Feynman theorem. Just rearrange my screen slightly so I can have a better view. All right. So let me just briefly remind you, we had as a first chapter the introduction, which we just finished, and we would now like to move to the second chapter in this course. And that chapter is called Theories and Postulates, Theorems and Postulates. And these are the postulates of quantum mechanics. All right. This second chapter is quite a lengthy chapter. It contains a couple of chapters, right, subsections, and I'll tell you about them now. The first one is an introduction in the technical sense. Yes, it's a technical introduction. We will repeat some of the very basics, which you should have already encountered in your introductory PC courses, so it shouldn't cause too much of a problem. And then we will quickly proceed to the subchapter called Hermitian Operators. So I like to use the acronym for this, HEROES. Okay, these are special operators, and we already briefly alluded to the fact that not all operators are equal, and some are very special, right? For example, the Hamiltonian operator has the variation principle attached to it, and we will build on this and strengthen this a little bit more within the second subchapter. The third topic is going to be series expansions. So that is a topic where we ask this question, what in German this is called Reihenentwicklung. Yes, how can we represent this wave function, right? It's this weird function in space, so you need to put something there, right? Some mathematical function you know already, which has to cover that region in space somehow. And this might be a good function or a bad function, doesn't matter. we will be doing this with series expansions, right? And then we will discuss the consequences from that. As a fourth subsection, we will discuss eigenfunctions. Now, eigenfunctions play a crucial role. Why? Because we are dealing with wave mechanics, right? That's the whole idea of Schrödinger's equation. Once you accept that, it's a very obvious thing that we should be discussing. What's the point of these eigenfunctions and how do they behave? Then we will have a sort of less known topic. Very briefly, we will discuss parity. This is sort of a general education. It will be rather inconsequential for your future in all likelihood, but for the sake of completeness, we should definitely include it. The sixth point should be measurement. And the seventh point will be location. Measurements, of course, this is what connects us to experiment, and experiments are crucial for any theory, right? I would even argue, if as a theoretician you do not compare to experiment, it's a very problematic sign, right? If you encounter a theoretician who shies away from comparison to experiment, we should always, experiment is the ground truth, and if you don't compare to it your predictions, right, then you don't know where you are in with your theories. So that's a crucial milestone for any theory, is this question: how predictive is it really? And just as an example, when Einstein developed his theory of relativity, everybody loved it, but it wasn't until he had actually predicted the right point in time when people would observe an eclipse. That's only when people realized, okay, this theory actually describes reality better than what we used to have before, right? And that's, of course, the crucial thing. Any new theory should predict the experiment better than the previous theories. If it predicts it worse, then it might still be interesting, right? Maybe we can learn something from it, but certainly the most accurate theory you have is the best model of reality science has come up so far, right? Now, that involves, of course, the question of how do you measure errors, right? It's not always obvious, right? If you have just one experiment and let's say one wave number, then it's easy to compare. But what if you had multiple experiments, right? Like multiple molecules. For one molecule, your theory is really good. For another one, not so good. Right? So then how do you average that one out, right? You just use the mean error. Do you say one molecule is actually more important to humanity than the other molecules? So that error should matter more, right? So then we are discussing very tricky things in detail. But what is certain is that a comparison to experiment should and must happen. All right, and then as the eighth and last, maybe most important subchapter, we will discuss the postulates of quantum mechanics. Okay. And that is what will constitute our second chapter. Any questions so far? All right. Then we will proceed to our first subchapter. So we are now in 2.1 technical intro. All right. So we will discuss definitions. We will discuss derivations. We will be doing a lot of math. I would recommend you to use a pen and an eraser in case you make the wrong notes, and to pay very much attention to the details, right? So when I change indices, when I change notation, usually this means something. Maybe either it means I made an error, or it means it's there for a purpose, okay? So really be very careful and attentive when we now discuss these formal relationships, right? Because that is, of course, what lays the basis of all future derivations. It also means you can view these indices and symbols as some part of a scheme to torture you, but you could also view them as something that is meant to help you, right? They have meaning, they carry meaning, and you asking yourself, what is the meaning of this index, is a very healthy question to have, as particularly as a university student, right? So that's part of the self-studying, that you ask yourself, what is the meaning of these objects we are discussing here? All right, so our first quantity, and that is not an arbitrary choice, right? That's maybe the most crucial quantity in this entire course, maybe in your entire studies, is the expectation value, right? In German Erwartungswert. Now, maybe you forgot how it is defined, right? But you can think of it as, so it corresponds to the average of normalized functions. Now, you know what's an average, right? You sum over something, right? And those are your summons. And if you assume, of course, infinitely small, arbitrarily small indices, then you know that in this limit of d going towards 0, you know that this becomes then an integral. And here we sum over our axis. And here we have our function, right? So and the average then is typically then you still divide by the total number of your terms, right? And that's sort of what's implied by normalized function. So this n, you can pull it inside, right? And so you can divide this, and this means you have a normalized function, right? So it's important for you to understand this expectation value is really just an average, right? That's what we are talking about. When we integrate things out, we also say we average them out, right? So mathematically, if this is not obvious to you, think about it, yeah? You should be able to figure this out by yourself or look it up in a math book. Anyhow, so in our notation, the expectation value then of an operator, right, could be written in bracket notation as something like this, okay? So this is bra and ket. This is the operator A. And these are our normalized functions. So this is how we write an expectation value in quantum mechanics in the electronic structure context. This is the same, right? So I use 3 dash. It's identical. It's a notation, which means the following: you integrate over your variables tau from -infinity to +infinity. Now, what is tau? Tau is the collective spatial and spin variables of all your electrons. Okay. So in our Hamiltonian, which we discussed in the introduction, this would be all the small r's and the spin variable, let's say sigma. Right? So we said you have x, y, z for each electron plus spin variable is 4 variables, and then you have n electrons. Okay, so this is a 4n dimensional integral. Corresponds to 4n dimensional integral. All right, so now we are starting the integration, and I like to write the dx, the integration variable, I like to write it to the left next to the integral symbol, okay? That's a notation thing, it's a style thing. You can handle this any way you wish. My reason for doing so is that I like to think of integrals as something that comes from the left, and I, like an operator, I do it to everything that's on the right, okay? If I want to stop, of course, I can close things with a bracket, that's that. You can do this any way you wish. This is just a notation, a preference I like. I find it more convenient, right? You might want to profit from that opinion and the kind of expertise it reflects. But you can also do it in other ways. I don't really care. All right. So now we are integrating. What are we integrating? A function. And this function refers to a state, right? And I like to call the state M. So that's the index I give it to you. And now you might wonder, hey, wait a minute, what's this M, right? Well, M could be, for instance, you have multiple molecular orbitals, let's say, right? So it could be one of them, right? Think of it as one of the orbitals, right? So that's one orbital. There's this convention also that the left, so this Fm, right, in the bracket above, it just becomes M, and it's the left, on the left of the operator. And that is the complex conjugate of F, right? That's what the notation above implies. Then comes your operator. And now I put the hat on it just to make it really explicit. A is an operator. And then comes the function n, little n, right? So if F is not mentioned in the bracket, it means that on the left, you have the complex conjugate of F for state M, and on the right, you have the complex conjugate of F again, but this time of N. Not the complex, the real part of N. Right? So that's what this integral means. Now, let me just make this a little bit more explicit. Of course, your F, your A, and your F depend on tau, right? your orbital depends on the space, right? It's in there, and it depends on the spin, right? If you change the spin, you'll have a different orbital, right? So that's how you can think about this. Now, we also call this if you think about the different orbitals, right? There are many orbitals in your molecule. And now you're combining the one of the left from the complex conjugate, the M with the N. So you can think of a matrix of M and N, right? So these matrix elements we can also write as A, M, N. This is also known as matrix element. Now, if you walk through the corridors of the chemistry building and you walk by two theoretical chemists and they are talking about their matrix elements, chances are they are referring to something like this integral. Okay, so a reasonable question then would be what are matrix element of which functions or of which operator, right? The A operator, what's your A operator, and so on and so forth. So this is the complex conjugate for completeness. Of the function f. Now, before we go into the break, we should clarify one thing. We work really on a problem, it's really tailored towards the electronic structure, right? And we assume, and that sort of distinguishes us from the pure mathematics, we make certain assumptions which make sense in the physical chemical sense, right? And these assumptions include that this is really, it corresponds our matrix element, our expectation value, right? It corresponds to a definite integral right? So we can integrate this thing. Right? And mathematically, you cannot integrate everything, right? There's some functions you cannot integrate. So here we assume it's integrable, and we can we integrate over space and spin, right? Of differentiable and continuous functions f. Now, if something is differentiable, it means I can derive it as many times I wish, right? I can get the slope and the slope of the slope and the slope of the slope of the slope, etc., etc. And it's also continuous, so it will also be smooth, right? So in other sense, these functions are very kind, right? From any mathematical operations, they will not do crazy things. So this is something which, of course, mathematicians find boring. We love it because it makes our life much easier. And there are many steps and derivations that rely on this assumption, right? So that's why we also need to bring it up here. We also, so basically in German, you call this gutartig, huh? So we have kind functions. This integral is definite. Why is it definite? Right? It's definite because we consider here matter, which we assume to be finite. Right? So if you go from infinity to infinity, it means there's no matter left, and all your matter is in the somewhere where you have your integral. Right? So if you have your space, let's put our tau variable, and here's the particle axis, the density. How many particles do you have? Let's call it a rho for our electrons. And here you have some molecule, right? Okay, so that's a projection, a 1D projection of your electron density. And then you know, well, this is sort of the molecular diameter, right? And that's how bad as it gets. And afterwards, if I add another times this diameter, there's nothing left, right? So if I integrate from left to right, from minus infinity to plus infinity, I will get some finite definite value for this integral. So that's what this means. It means it's compact, right? All right. Any questions so far? Doesn't look like it. It's 10 o'clock, 2 past 10, 2 past 11. Let's have a little break and let's reconvene at 11:15, please. Okay, let's continue with the lecture. So we just introduced this notion of the expectation value of this matrix element, and I'd like to alert you of the fact that we tend to be sloppy and lazy. So, for example, if, as I said, if in both cases you have the same function, right, we skip it in this bracket, right? So instead of writing this, right, we like to abbreviate it like this. Now, of course, if you didn't have the f function in both cases, but just some function of some state, right, then you cannot do this anymore, right? So this notation, this shorthand notation here on the right, it already implies something, right? And we can do it for convenience under this condition. It's f on the left and on the right. That's not generally true. And so if it's not true, then you have to make it more explicit. Now, we should note something that if we have this expression, so let's say note, right? If we write our integral now without the operator, just for the function, right? So complex conjugate on the left and on the right hand, the real part. That is the same, of course, as saying fm, fn, right? Another notation is also to use these curved brackets. That's also fine, right? Or as we just said, mn. Now, as you can see, I have here complex conjugate on the left versus the real part, and it's just multiplicative. I can flip that, right? So this means that in this case, this is all the same as saying NM and then doing my complex conjugate here. Okay. So that would mean, so let me write that out. If I flip this side, I must do something like this, okay? So this is basic bracket notation, and I hope that that is clear, but just as a reminder here, and that is our first node A, and I'd like to add another node B. So that was just on the two functions, right? Now, what if we have an operator in there too, when we talk about the expectation rate, right? What happens then? So suppose you have some prefactor CF, where this is just a constant, okay? And that's in front of your F, and your operator, and then G. Well, the bracket denotes just an integral, and the constant can be pulled in front of the integral, but it's part of the complex conjugate function part, right? So this is the same as the complex conjugate of the C, F, A, G. Similarly, if you have this situation that G is, that C is in front of G, then it is in front of the real part. So when you pull it out in front of the integral, there's just a real constant C and not its complex conjugate. All right. Again, if you have questions or comments, please unmute yourself and interrupt me, or paste your question and type it in the chat. So we discussed the expectation value, we discussed the bracket notation, we discussed the space we are considering, we discussed how things look like for these complex conjugate functions. And with this, I'm through the subsection of the introduction. I'd like to maybe still remark once more, we do have to deal with the wave mechanics of the electrons due, among others, but maybe historically most importantly, due to the double slit experiment. Okay, this experiment can only be explained by the dual particle wave nature of matter, and this is an experimental finding. You cannot reject that. You cannot say, oh, this is annoying, I don't like wave mechanics, this is not up to your choice, this is how reality is, and so we will have to deal with this. And so these assumptions we just made, right, about your functions being kind, so this is what we are applying to these wave equations, right, to these wave functions, right. Now, the finiteness we also discussed above. also results or basically implies that you have a potential in your Hamiltonian that is spatially finite, and so you have some constraint in terms of where things can be, right? And now you should all be familiar with the particle in the box solution. You should all be familiar with the harmonic oscillator solution. You know that as the length of your box, as the curvature of your potential, as they come together, the discreteness of your solutions emerges. Right? So it's this combination of the wave ansatz due to the double slit experiment, together with the spatial constraint of your system, the spatial size, right? Now you could argue, well, if it's infinite, then we don't have a quantum solution, and then it's just flat, right? There's no wave. And that's correct, right? Mathematically speaking. But then you have to ask yourself, is a molecule spatially finite, yes or no, right? And again, experience shows that it's spatially quite finite, right? So we have to impose, to get reasonable answers to chemical questions, we have to assume spatially constrained potentials. The spatial geometries of our system is finite, and from that follows the discrete quantum nature of our solutions. All right, I'd like to go now to subchapter 2.2, which is the Hermitian operators, right? Which we like to call heroes. Now, there's I'll start with a remarkable statement which says that all QM operators are linear and heroes. Okay. Now, that is an amazing statement. This is out of experience. We know this from experience. Like Newton's first law, we never have observed anything to the contrary. It's incredibly impactful. You might not yet realize, but it is impactful, and hopefully later on you will see. So it has an amazing impact. Okay. And it happens to be extremely relevant for your exam. I point that out every time I've been giving this course over multiple years now, and every time I point that out, and still, to my surprise, there's always a fraction in the student body who somehow doesn't get this. Every time I try to phrase it more carefully, of course, because of that, but I'll hope that this statement also, this comment, makes you extra alert now. Now, what does this mean, linear and Hermitian? I mean, I throw these words at you, and you might be saying, well, I don't know what he's talking about. I presume you know what's an operator, and I presume you more or less have an idea what I'm referring to when saying QM, but what is a linear operator, and then what is a Hermitian operator, right? So a linear operator, that's the easy part. So what is linear? Linear simply means that if you have an operator that acts on two functions, right? It's basically, it's been factored out, right? So you can write it like this. And reversely, right? If you have a bunch of terms that result from operating the same thing on them, you can factor out that operator. So that's what linear means. It's not obvious that that should be the case, right? That you all operate. Imagine, for instance, some operator which raises things to a power. Okay, that is mathematically certainly permissible, and it turns out in quantum mechanics we don't have that. So that's really nice. Okay, it makes our life very, very easy. It's typically underappreciated that we all profit tremendously from the linearity of all QM operators. Now, what about being a hero or not? So what is a hero? A hero is an operator whose expectation value is real, right? So any operator A for which this is real, not a complex conjugate. And as you can see, I did not specify the functions, right? So it means I could also throw in some complex conjugate functions in there, right? But still I would get a real eigenvalue. Let's spell this out a little bit more. This A, right? This expectation value is our d tau. And now we didn't specify the function, so let's presume some wave function. So let's call it psi. Psi star A psi, right? It wasn't specified which function to use, so we just set one, right? That's fine. It's still, that's what's being implied in this bracket notation. That's why it's so elegant, right? Now, we can say, because it's real, right? Your A could operate on the conjugate or on the real side, right? So in other words, we could also say you will get the same eigenvalue, right? So we can say that psi should operate to the right. And so now to the right of the complex function. So if A was not Hermitian, then you would get, you could possibly get an imaginary or complex conjugate eigenvalue. But because it is, it's not, and that's why we can write this last equality sign. And that is also the same as saying, so this is because eigenvalue of A must be real, right? And then, so this is an identity, and this is also an identity then that tau this one, right? And that means this, right? So as a first consequence of the eigenvalue being real is that the expectation value also be real, meaning it's the same as for the complex conjugate. Okay. Now, this is sort of a consequence of the definition we've had, and this is not the definition itself. The definition is that it has a real eigenvalue. Okay. Now there's another consequence, right? So this you could call the first consequence. Let's look at another consequence, right? And this is a part of being impactful, right? It's quite abstract, but because it's so abstract, it has so many consequences. The second consequence is if A is Hermitian, right, is that it can act to the right or the left, independent of the function you're using. So that's quite crazy. Now, let me write this statement. Hero can act to right as well as to the left, right? So first of all, operators always work to the right. This is this should be a reflex, right? So if somebody comes along and says, well, you can go both ways, right? That should make your hairs go up, right? This is a really scary statement. And so this deserves a lot of thought, right? We will discuss this now in more detail. So this means really this second consequence. So in other words, the expectation value of some function, some complex conjugate f, with the operator and some function g, right? Not the same function, any functions. This thing is supposed to be the same as G and then A working on F, right? So now it's properly written, right? So mathematically, we always apply the operator to the right. So if you're saying we operate it to the left, you write it, you flip places, right? Such that it's written to the right. So that's the statement in mathematical form. So that's the crazy person telling you heroes do that, right? This is an equality sign, and you should be a skeptic and you put a question mark here. Really, right? Is this true? Now let's see if we can show that this is true. Right? Let's prove you wrong. So this is quite unbelievable, but it's true. So let's put it here, unbelievable, but true. Okay. And how so? So because, consider this, consider the following. Let some function psi be f plus c times g. where C is again some arbitrary constant. Okay. So basically, we construct a linear combination in these functions f and g we just used, right? So that's something we can do, right? Nothing in the statement prevents us from doing so. And now we'd like to consider the left-hand part and the right-hand part of this equation, okay? So let me put here a little raised bracket and here as well, right? Okay. So if we insert this, right, then we have here on the left the tau f plus cg star a f plus cg. Okay. And then this is supposed, question mark, yeah, is supposed to be equal to the right, right? So I keep this equation sign with the question mark just so for your clarity. What's happening on the right? We have the same insertion, d tau, and now for g. Oh wait, I skipped a step here. I see right now. We will. There's something I didn't say. In front of this bracket, actually. Yeah. Okay. I'm sorry, I didn't clarify this clearly. I want to use what we said above. So what I'm going to do is, I'm sorry. I'm going to use this expansion for my psi, right? And I will write my A from here above as my d tau psi star a psi, yeah? So using this and using this expression for psi, right, I can combine these two to obtain the expression to the left and the right here. Okay, I'm sorry, this was a bit, I missed that, I forgot about that step here. In between, we need to keep that in mind. So this expression here is just our psi star psi a, okay? And on the right, you do it in complete analogy. Here on the right, we have our A star. Okay, that's going in here on the right. So our A star is F plus CG. That's our psi. Times, and now we have A acting on F plus CG complex conjugate. Okay. All right. So now we have these terms, and we can simply factor them out. So this is the left-hand term here. So let's write the left-hand term. The left-hand term becomes B tau F star A acting on F. All right. Then we take the CG, and this CG carries a star. So I have a star, the complex conjugate of C, and the complex conjugate of G, and that has to be multiplied with A acting on F again. So that's the first two terms, and then I have two more terms. Now A acts on CG, so I pull the C in front of it, and then I come from left with my F star, and then my A acting on G. Okay, and then I have the term with the two CC. So one is complex conjugate, then I have my complex conjugate G, and A acting on G again. Okay. Now, this is what's happening on the left-hand part and what's happening on the right-hand part. The right-hand part would be B tau, and now we have F times AF star plus CG with AF star again plus, and now we have the C, which again we pull from the right over. So this is the complex conjugate C, then F from the left, then A acting on the remaining G complex conjugate. And then finally, again, the cross terms, C star, C, G, A acting on G complex conjugate. All right. Now, what you can see is that if this equality holds with the question mark, we have the same terms on the left and the right. Right? So if that equality holds, if that question mark is to be answered in the affirmative, then we can cancel some terms. In particular, this term and this term for the Hermitian operator are the same, right? That's what we discussed above, right? So now it's the same function f, right? And similarly, the last term here, right? So these terms cancel, right? If our operator A is Hermitian. And so this means our equation reduces or simplifies to the remaining terms. So on the left-hand side, we have C star G star A F plus C F star A G. And I keep my question mark. E tau CG AF star plus C star F G star. All right. So we got rid of 4 terms in total. And now we can, this was just factoring out and simplifying, right? So it's a little bit tedious to go through all these factorings, but one has to be careful. We always pull the constant in front, but we did get a substantial reduction in number of terms. But what we haven't exploited yet is our expansion of psi in this linear this linear expansion of linear combination of F and C and G, right? And this is something we can still exploit now. So we want to exploit this in 2 ways, right? The first, let C be equals to 1, a real, and this one also equals to the complex conjugate. So no complex, right? So in this case, if C is a constant, right, and if C is equals 1, right, then what happens is that d tau from the left hand again. So I'm on the left hand again. So C is the complex conjugate C is 1, right? So I'm left with G star A F plus F star A G, right? That's what's happening to my left hand term. And my right hand term will become d tau G AF complex conjugate plus F AG complex conjugate. All right. Okay, that's pretty easy. But now we apply a little trick, and we're going to say, consider now the case that C is equals I, right? Our imaginary number, which means our complex conjugate, of course, is minus I. So we set C equals I, and then what we also do is we divide the equation by I. So hang on, I still have to keep my question mark. So and divide by I, right? So this last step, the division by I, this is very common. Like this, you get rid of your complex numbers, right? So this means then that our equation here becomes minus, so again, this is the left-hand part, minus d tau, right? I pulled out the C star, that was minus I, and then I divide it by I, so that leaves me with a minus. So I have minus d tau G star A acting on F. And then there was a normal, not the complex conjugate, a normal C here, right? That one becomes I, right? So when I divide I by I have plus 1, but I put my minus in front of the integral here. So to get my plus again, I have to put in a minus. And so I have here F star AG. Okay. And that's what happens on the left-hand side. What happens on the right-hand side? We pull out the C. That's I divided by I is plus 1. So our sign in front of the integral does not change. But you had a C plus in the second term on the right-hand side, and that, of course, means there's a minus I divided by I is minus 1. And so I get this change in sign. And what you see nicely illustrated here is that the use of the imaginary number, really, the main point of it is that we can introduce different signs. Okay. And whenever we can do this, terms might cancel. And this is what you're going to see now. We're going to add these two equations, right? So our equality symbol with the question mark should also, if it's true, it holds also for the sum of the two left-hand and the two right-hand parts. And so what do we get then? Now let's collect some terms here. Right? What happens to our left-hand term? Well, we have the integral over d tau, of course. And then the first term, G star AF minus G star AF. That one cancels. So we don't need this. And then we have F star AG minus F star AG. So 2 times F star AG for the left-hand part. And this thing should be equals. And now we look what's happening on the right-hand side. We have GAF. Of course, again, d tau. We have the GAF complex conjugate 2 times again. And the F part again cancels. Right? So what you see here is that if you're allowed to operate, right, like we did here with the Hermitian property, then of course these two 2's they cancel, then this must hold. So this is FAG. Okay. This is the demonstration, right? That this holds as a consequence of the fact that up here we wrote down this. we inserted our expansion of psi, and we see that if we operate with A to the left or the right, it's the same. It's the same. Now, as a question, could one also say before canceling terms, I guess before the inserting the C's, probably referring to this equation, that right hand equals left hand complex conjugate. Yeah, I guess that should also work, right? If you do that, yeah, that works as well. That's a good point.
If you guys would like, we can also go over a geometric example that demonstrates this in the exercises. The cool thing about quantum mechanics is there's like many ways to show the same property.
Yeah. All right. It's 12 o'clock. Are there any questions? If not, I'm gonna end the lecture now. Tomorrow, yes, please.
I just have a question for Morris. You sent an email with I think YouTube videos of, I think you said you should watch the first 30 videos, and then after that, you can watch them singularly again, I think with every lesson. And I'm just not sure after the 30th video, which videos or how many I should watch a week.
This is totally up to you. Some people individually asked me for some external videos that I found helpful. So I just shared what I found helpful to me. So there's certainly no requirement here, right?
Yeah, I know. Yeah.
It wasn't clear.
Yeah.
So speaking broadly, those videos that I shared, their titles are pretty much in line with what we'd look at. So if you're confused by any aspects of hermiticity, then you can click on the hermiticity video, right? Later on, when we get to variational principle, the same thing. So those are simply like an addition. So when I said watch the first 30, that simply means that where we're starting now corresponds more or less to video 30. So it should be relatively self-explanatory in terms of what's relevant. Again, that's only if you feel like you need additional help, right? Fundamentally, these lectures plus the exercises should be more than enough. But that was in response to specific questions about additional videos. So that's why I sent that email.
Yeah, okay. So there's no real schedule as to
No. I'm sorry. There's no. This is totally if this is something that you're interested in, this is something that you can do.
Okay. Thank you.
Sure.
All right. So thank you so much for your attention, and I'll see you tomorrow.